Yes. Marisa, second. Okay. Yes, I can mute all. Yeah, in case. It's 9. I think we should start. Yeah. Maybe let's see. Wait a couple of minutes and then we start.
Yeah, probably can just start. Close the door.
Yeah, there are 5 or 6. Okay. Then you can start. Admit.
Okay, so you have to admit.
Yeah. Mattia. Ci sono persone che stanno arrivando. Tu puoi fare admit, perché non posso adesso che...
però io ho fatto te e devo ricollegare. Aspetta. Il problema è uno che non ci sono, there are no plugs around, so my laptop is going to die after a while.
Okay.
We do that, yeah, but can we, we should be here.
Okay.
But can we ask the people outside to, or maybe I will just change edit the, let me see if we have the option to, we should start.
Yeah, we should start.
Where is the...
We should start.
Yeah, now there should not be any waiting room anymore.
Okay.
I don't know if you have to be there. Maybe not.
Okay, I think we should start. So maybe okay. Good morning, everyone. I'm really very happy that many of you came today for this seminar on solar energy planning. I know that I need to do the acknowledgements at the end, but I'm really afraid that I can forget some of people. So I need to acknowledgement many people. First of all, NTNU team, Anne, Cordula, Ula, Maria Fernanda, Vegard, that they helped a lot during the organization of this event. And I need to thank the Norwegian Research Council for financing part of this event. And the other part has been financed by Multiconsult. I don't want to take more time, so I give also the chance to Tobias to say a couple of words. But thanks a lot. I hope that you enjoy the presentation today and the discussion.
Thank you, Gabriela. I'm Tobias from Multiconsult. Just want to welcome you all. And we have a great set of presentations today, and I hope we can have good conversations and discussions today. Thank you.
Okay, so we are ready to start. First speakers. Is Maria Ball. This event is also organized in the framework of Task63, Solar Neighborhoods Planning. Maria Wall is associate professor at Lund University, and she's the leader of the International Energy Agency, Solar Heating and Cooling Task63. She's an international expert in different aspects related to energy efficient building, solar energy strategies for building and urban areas. So in the meantime that Maria, you just take this. You take this one?
Only
okay.
5 minutes.
Okay.
So I think it takes the same time to put it on and off back. 5 minutes. Thank you, Gabriel, and all the organizers. It's really nice to be here in Trondheim, and we have been here all week. I'm from the south of Sweden, and it's nice to see snow because we seldom have it in Lund where I'm from. So that's great.
Sorry. Just one more thing. I share the screen now online as well for who is connecting online. I hope it works. Please, Maria.
So
yeah.
I can use this name.
Yeah.
So I will just give you a brief overview of this project called Task63 on solar neighborhood planning. And solar neighborhoods, what's that? Well, for us, we have been quite broad in the definition. So a neighborhood for us first is defined as a group of buildings, a district, with a specific geographic area, often including different types of buildings and functions, open space and infrastructure. And the neighborhood can be part of a larger city, but also an isolated community or something in between. So it's really a lot of things. And it could be connected to a district heating or cooling network, or outside such. And this gives, of course, very different boundary conditions when we look at the energy concept. So the solar neighborhoods then here I want to get the light on all the benefits we can have using solar in neighborhoods. So we can use it for passive solar energy, both indoors and outdoors, to reduce heating demand and to improve thermal comfort and health. We can use it for daylighting buildings and outdoor areas. And in this way, we reduce electricity for lighting and we improve visual comfort and health. And we can use it, of course, to produce locally the energy production using PV and solar thermal systems. And in this way, we can create energy and resource efficient, self-sufficient environments. And we then don't have to rely so much on energy imports. And we can create resilience to energy price fluctuations. And today, this is really relevant in many countries. We can use it also for local food production and green areas for improved air quality and reducing stormwater. So there is a lot of things here, a lot of benefits, but we don't do it as well as we could, as much as we could. We don't use it as much. So there are good examples and you will see a lot of them today, but we need to do more. And that's why we started this project, Task63, on solar neighborhood planning. It started in end of 2019 and it ends end of this year. So the main objective is to support key players to achieve solar neighborhoods, to facilitate the long-term solar access. And this should result then in sustainable and healthy environments. And we deal with both new neighborhood developments and existing neighborhoods. And we work on all the aspects I mentioned about solar energy. And it all relates, of course, to energy, environment, economy, and the inhabitants' comfort and health. We are organized, at least try to be organized in 4 subtasks, and they have different leaderships. So for subtask A, on solar planning strategies and concepts, we have a Canadian leadership. Subtask B on economic strategies and stakeholder engagement, we have an Italian leadership, and Silvia's here today. We have subtask C on solar planning tools. It's jointly led by Sweden and France. And Yuri and Martin are here today also, you will meet them. And we have the subtask D case studies that is dealing with all the other aspects from the other subtasks. That's led by Norway. Gabriele and Mattia are here today also, of course. Sorry. And you get some support from the other leaders as well. And then I'm the overall project leader. We are 9 countries participating in this project, from Australia, Canada, China, and then some European countries. And I don't say more now. You will listen to all the experts presenting. You can see here there is a link to the task website. There are a few publications already. There will be more in the next 12 months, I would say. And you can also visit a few finalized projects that we have been working on earlier. Task 51 on solar energy and urban planning, and Task 41 on solar energy and architecture. And that project was on the building scale level, not urban planning. So thank you for that.
Thank you, Maria, for your presentation. We go ahead with the program. The next speaker is Steve Voller, Associate Professor at Sustainable Energy, Electrical Energy at the Department of Electric Energy and Manager of NTNU Energy Team Solar. He has a lot of experience in integration and wind energy into the German market before moving to Norway. And he was postdoc and then researcher for NTNU and Sintef Energy. So, Steve, the floor is yours. Before you start, and I forget, thanks a lot to all the speakers to commit and come. I really appreciate your commitment, especially to Robert and Gail. That was a very short notice. So thanks a lot.
Thank you. I take this.
Okay, yes.
Yeah. So I'm working at the Department for Electric Energy. And I'm talking about Team Solar. Team Solar is one of the teams that NTNU has. So NTNU has 4 strategic research areas. One of them is energy. And within the energy, we have different teams. And the main goal of the team is to collect all the people working at NTNU with one topic. So we are collecting all the professors, PhDs, master students, bachelor in a team. And we try to work together on the topic solar or on the topic hydropower or whatever. And this is working very well, I guess. So before we had the team, we were a lot of people spread around at NTNU working with solar. And if you look at the topics, you can see that we are covering all the aspects of solar, so the whole value chain. So we can do things in physics, yeah, like silicon cell production, testing of new materials. We have technology, so we have solar panel design, integration in buildings. We have architecture, looking at the shape, the form, color of solar cells, how they can be integrated. We have people working with mounting systems, both in buildings or floating solar or standalone solar systems. We have people looking at fire safety, which are here today. And then, of course, my field, the integration, both the power and the energy produced by solar systems. Market integration, the different types of solar systems what we can use. So integrated in buildings, in the roof, facade, mounted on the ground, in combination with agriculture, floating solar. And one of the main aspects we are doing is looking at the Nordic conditions. So there's a lot of research on solar in the world, but there's only limited research on solar in Nordic conditions, meaning mechanical stress due to the snow covers, reflection from snow, temperature, daylight. Yeah, we have month without light, we have month with just sun. And how is this working in Norway? So how can we make solar attractive in Norway? How can we use solar in the north of Norway and the south? So it's not just one fits all like in other countries, but it's very dependent on the climate conditions here. So this is one aspect. Now, of course, we have digital solar electricity. So looking at prediction, big data, measuring RE integration in the whole solar chain, looking at business models, and for example, also communication, power electronics, which is a very important part here. And then last but not least, the acceptance is very important. We are mostly engineers, so we are like to just say what is good. But if it's not accepted from the people, both in the buildings, in the urban environment, large solar parks in the landscape, then solar will not succeed. Today, we have around 24 professors from all the fields at NTNU and 18 PhDs and postdocs. And this is a growing field, so it's a plus and plus plus. So here I just listed the postdocs and PhDs working directly with solar, not counting those who has solar as a part of like the thesis. So these are the only ones really focusing on solar. And if you go through, you will see we cover all the topics I mentioned on the slide before. So we have integration, we have architecture, business models, digital, and so on. We get approximately 5 to 10 new solar PhDs in 2022, 23, 24 also. And we have approximately 20 to 30 bachelor master theses just dedicated to solar. And this is also very important because a lot of students want to work with solar, and the industry is also looking for candidates having solar. And I see a lot of faces here from professors and PhDs and former and actual master students. Yeah, so this is nice. So what we do, we try to collaborate so that not only the people on electrical energy are working with solar, but we want to have projects together with other people. So solar integration and acceptance, for example, or acceptance and architecture. So we try to combine the people in our group. One project we tried is the social acceptance, but wasn't founded, but we try again. Then one is on agri-PV. So this I will show later on a new slide. And then of course the Helios project. These are just some I mentioned. There are much more where we collaborate. Then we try to work together with other people outside of solar because solar alone is not working. So we need a hybrid system, solar and wind, solar and hydropower, and so on. So we'll have also combinations with other teams and other people both at NTNU and outside NTNU. We are a contact field for industry. So we like to get contact with industry. We help our PhDs and students get into contact with companies, get the data, be a part of research projects and so on. And here we also have a lot of master and bachelor topics. We are trying to push solar up in Norway. So we have a lot of national projects, Forskningsfond or Enova or the Research Council, for example, but we're also aiming, of course, for international projects. Then we have a good collaboration with Research Institute SINTEF, which are located in Trondheim at the campus. So we have an own center combining Team Solar and the team at SINTEF that we can work together. Very good. And then in approximately 2 years, the Research Center for Solar will be finished. So we need a new one. So we are working on a new FME on solar in Norway. And I guess we will get it somehow. What we do is dissemination. So like today, standing here and talk about solar, go out, make solar great in Norway, because there's still a need to tell people that we have solar in Norway and sunshine, and that it's worthwhile to invest in solar. And then, of course, we want to increase the education at NTNU. So more students get known with solar in different aspects like power engineering, architecture, construction, and so on. Because we think this is a topic that will come in the future. What we do is, for example, get an overview. What do we have about solar on NTNU? And we found out we have quite a lot. So we have different installations. There's one installation at our department with 12 different angles. So there's a lot of research that can be done here. Then we have the tracking system from SINTEF. Bifacial, so there are also some master students working on that system. And there are, of course, many things what you cannot see, like the Smart Grid Lab or the Daylight Lab or the solar simulator. And then, of course, all the buildings from SEP and SEN. So also here we have a good collaboration between the people involved. SEN building is also very attractive for research with all the different angles and the integration in the whole system, like energy storage and so on. And then one of the projects I'm proud of is the Agri-PV project we will do in Shetland Skole. This will be the largest in the north and the first in Norway and the northernmost installation, consisting of 50 kilowatt. So it's not much, but still it's the largest one. And here we want to see at both energy production and crop production and how this solar installation will influence the microclimate. Yeah, so we are working close together with the school. School is an agriculture school, so we are also involving the pupils, measuring the grass, clipping grass, and measuring the weight. And first studies showed, okay, we will lose around 10% of the grass, but we can still produce 80% of the energy compared to a whole just solar installation. So this we find out, and now we will build it. So is it in construction? So we hope we can get the first data in the summer, and they will also get the battery system now. So this will be a very nice living lab for us. Okay, that's all. So if you are interested in solar, working at NTNU, our students, our company, just contact us, Team Solar, if you just look it up. And then we will find the right person you can collaborate with. Thank you.
I think, Steve, you save 30 seconds. So
yeah.
There is any immediate questions from the audience. Or for Maria as well. If you have any questions, don't be shy, please. No questions?
Yeah.
I see many students here.
I'm here the whole day to just come and ask.
I see many students, so I think you should take opportunity. He's the leader of Team Solar, many topics, so please take contact later on. Okay, so if there are no comments or questions, we go ahead with the program. Thanks a lot, Steve. So we start with the first session. Let's see. Okay, next speakers is Robert Hall Lund, civil engineer and Master of Science in Energy and Environment from NTNU with specialization in heat pumps. He worked in Skanska since 2017. You have many competencies. Maybe you can tell in the meantime in the presentations. Yeah. Because are too many.
It's very broad.
Yes, it's very broad.
But solar is one of them.
Yeah. Yeah. So I leave the floor to you. We are in a special building, Powerhouse Braterkaya, and Robert will describe the secrets of this building and the challenges that you had. Thank you. Floor is yours.
Yeah, thank you. So my name is Robert. I work at Task63. We are the in-house consultants for Skanska. And I will talk about two things today, mostly about the building we are inside now. And then a little bit about the microgrid that this building is connected to. So, Skanska, we have high ambitions in our climate work. So we will reduce our greenhouse gas emissions by 50% by 2030, and we will be climate neutral by 2045. And the building we're inside now is a part of that journey. So we have gathered a lot of experience developing a project like this, which we then use for further buildings that we now build. And the building we're inside now is Powerhouse Braterkaya. It was finished in 2019, so a few years ago. And the customer is Entra AS. They also own some other buildings in this area. The architect is Snøhetta, famous architect company. And then Skanska is me, the construction company that built this building. And what is a powerhouse? So this is the original definition that this building was built upon. And very simply, during the building's life cycle, which is 60 years in this case, we have to produce more electrical energy than what the building uses for operation, and also the energy that went into the materials, transportation of the materials, and also the end-of-life disposal of the materials in this building. So there's kind of three things in this equation. And maybe the most important part is that we have to produce a lot of energy. And this whole building is actually designed to fulfill that goal. So you see the roof is inclined. I believe the inclination is 19 degrees to get a nice angle towards the sun. And the whole building is oriented towards the south. So the orientation is also not just random. And you see that even though we have the whole roof covered with solar panels, it's not enough. So we also have panels on the southeast facade and the west facade. And how much are we going to produce? So you see at the left side there, there's the calculated solar power production the first year, which simulation shows what's going to be 458,000 kilowatt hours per year. And now that we have operated this building for since 2019, we see that we have not yet reached that number. And then the question is, why haven't we reached that number? Is the weather, has it been bad the last 3 years? Has it been more rain in July than we anticipated? Or is the climate model used for simulation maybe too optimistic? I don't have a definite answer yet, but I think it's a combination of both. So we will continue monitoring this building's operation and then the building's energy production. And then we can see when we have more data after many, many years, is the standard year that the simulation gives us, is it actually, is it good enough? And here you can see the production. So the red one is the roof, and the green and the burgundy one is the facades. You see the facades, of course, have peaks different times during the day. And so this is in April. And then we're almost at 400 kilowatt hours of peak production. So that's the production part of the powerhouse equation, but also we need to use low levels of energy operating this building. And how do we manage that? So I would say the most important part is our thermal system in this building. So the heart of the heat system is industrial grade ammonia heat pump in the basement here, which uses the seawater in the fjord as the heat source. And the system is coupled together with our neighbor building, Task63. So the heat pump makes 50 degrees water, and then the other building uses the 50 degree water first. And then this building gets the return from the other building. So we use 40 degree water, and we heat the whole building with water at that temperature. And the heating system is, we recirculate hot air during the night. So there's no radiators in this building. It's only heated by the hot air during the night. And you see behind me here, there's a big exposed concrete wall. And this whole building is very thermal heavy. So we're able to accumulate a lot of heat during the night, which then keeps the temperature stable during the day and until the next night where we heat it up again. And also when you walk around here, if you see in the ceiling, there's a lot of exposed concrete in the ceiling. So we're able to accumulate a lot of heat. So here you see the thermal exchange. So first, the neighbor building uses the heat, and then this building uses the rest. And the third part of the equation was that the embodied energy of the materials used is also low. And for instance, in this project, Skanska developed a new type of concrete, which have a very low climate impact. That's one of the things. One of the things we did to have as little energy in the materials as possible. And so the next part is that this building is a part of the Bratterkaia microgrid. This is a part of the city exchange project. And since we have so much surplus energy from this building, we would like to share it with our neighbors. And as you can see here, powerhouse, our peak electrical demand is maybe 130, but at a good sunny summer day, we produce 450 kilowatts. So it's a huge surplus. And also BK16 have a little bit of surplus. So then we would like to share this electrical energy with the electrical buses. There's a bus charger just over there. You can see it when you walk out the main entrance. And also there are chargers in the basement for electrical cars. And there's also been talk in the future to supercharge the Coastal Express. And this is where we are now, the Brattørheim microgrid. And the components in this microgrid is what we see here. So we have two producers. It's this building here with this building here, and also the other producer is the DK16. And then there's 4 consumers, this building, and DK16, DK15, and also the electrical bus. And this grid also have a battery. You see the size is 400 kilowatt hours, which is maybe less than 1 hour of peak production, but it still has a value in this system. And this is the management principle of this microgrid. So we have a control system which can control the different parts of the grid. This system talks with the trading platform for the economic part of the transactions with electricity. And that trading platform talks with Nordpool. This is the idea. And the question is, why do we want a microgrid in the first place? What's the benefit? So the benefit is, as you can see in the left part there of this power duration curve, if we in a neighborhood level are able to peak shave our loads, so the battery can work, battery can spend its energy, if we can control when the heat pump starts, if we can accumulate heat in the thermal system, we're able to, in our neighbor area, decrease the electrical peak necessary to, decrease the electrical peak. And if there's a lot of areas like this in a big scale, the grid operator doesn't have to build out so much electrical grid because the peak is lower. That is a gain to society because we, as citizens, we pay for the electrical grid. And what we have learned from this microgrid project, the legislation is not where we want it to be. And now it's very difficult to trade electricity across property borders. It's actually very difficult, but thermal energy we can trade easily across the property borders. That's one part. And also, if we, in a bigger system, are able to see the electrical and thermal system in context, the whole area will benefit. So, for instance, if thermal system is built with a little bit extra accumulation, are able to accumulate a little bit more heat, maybe the heat pump can be turned off for longer periods of time, and the electrical peak of area can be lower. Yeah, that's my my short presentation. So thank you.
Thanks a lot, Robert. It was very interesting.
Yeah.
We'll have some question later on at the end of the session. I hope you can stay. You are quite busy. Okay, great. So we go ahead with the next speaker. Geir Ficke. I just repeat again, thanks a lot to you and to Robert, very short, let's say, information, but you managed to do that. Before you start to help with the microphone, let's say a few words about you. Geir Fikke is project director at Solar Energy Fusion IS since 2016. He has over 30 years experience as a product developer, project manager, and technology manager in both Norwegian and international business, as a consultant technology management for your own company as well.
Right.
Thanks. The floor is yours, Geir.
Can you hear me?
Can you try to speak, because it's yeah, if you can just put a little bit down. Yeah, the other part.
Okay.
Otherwise, yeah. Just a little bit down, close to your mouth.
Yeah.
Otherwise, you can use the other one.
Maybe.
Maybe, yes.
Yeah.
Yeah,
that's easier for me. Thank you.
You're welcome.
Okay, my name is Geir Fikke from Solar Energy Fusion. We are one of the main players with solar energy entrepreneurs in Norway. My boss, Christian, started the company 10 years back in time. So we had 10 years anniversary just some few weeks ago. And we are now seeing a tremendous growth in this market. So I will just give you examples of what we are doing, and you can imagine yourself what you can do with that examples. Yeah, we are making large roofs. So you can see down left, that's Oslofjord, 2.2 something megawatt. That's what we are doing. Mainly flat roofs, but also facades, big facades. On the right side, it's in a building in Oslo. It's a big facade in an urban environment. On the top is a picture I took when we started a blue roof at Allerek, close to Haukeland Hospital in Bergen. And in the middle down, it's downtown Kjøpesenter, a big place for, well, shops. It's an old factory building, and it's a very weak roof. So they had to shuffle snow from here or from time to time. But they don't have to do that anymore. I can tell you why later. So again, Bergen, and also I think that's a project in Oslo, to the left. In urban areas, we need to delay the drainage. You probably understand why, and especially in Bergen. Because when you're building new buildings, they have not enough capacity in a drainage system to take off all the rain. And then we have to just, well, they have to stop drainage a little bit. In this special roof, particular roof in Bergen, it was a Skanska project, by the way. And I'm so happy to work with Skanska, because you're one of the clever guys in this business. You told me it was 15 centimeters with water. That was the top level. If it's get more than 15 centimeters, then it will be a kind of overflow system that will take over. And then we had to lift the panels a bit. You can see the stones. They were lifting it at least 15 centimeters, so the panels will not be exposed to water permanently, and also it won't freeze. That was the case. If things freeze, what are we doing? Well, we don't know. We have to be on the safe side. We lift everything up. So sedum and blue roofs delays water drainage. Super important in cities. And if you want to know more about that, we have, Fusen has a blog, and you can read more about that in the blog. Facades, industrial and urban. On the top right, it's from Asko Hedmark. That facade produces more energy per square meter than the roof. Means that facades are super efficient. Depends obviously where you are. And also a cool picture of my colleague Anna. This is Oljedirektoratet, the Norwegian Petroleum Directorate in Stavanger. And they had to change their facade, and they changed from what they had to PV. White panels, black panels. Big panels. You can probably see the panel shape. One little, it's bigger, that one is smaller. You have black, you have window. A lot of different sizes. On the bottom left is Kiwi Dalvor. So if you are from Trondheim, I've been in Byåsen. This is one of my projects from 2017. This is thin panels, and this on the top is crystalline panels. We have also crystalline and thin on roof. And IFE, I also have made a lot of sensors, temperature, irradiation, wind on roof and in the facade. So IFE has made a report trying to find out if thin film versus crystalline, what is the best? I don't think, because the theory at that time was that thin film was better in diffuse light. They didn't find any proof of that. Then this is from middle, is just normal, nice facade in Bergsbyen in Fredrikstad. And on the right side, bottom, is Voldsbø School in Oslo. That is the coolest building in Norway with facades. Just opened. The panels, I think most of the panels are different. Some few panels are like, there are 3 different colors. Many panels also have 2 different colors in one panel. And they are not square, a lot of different sizes. So it was again, my dear colleague Anna, that was the project manager for that. And she spent a lot of time inspecting all the drawings from the architect and also follow up the glass producer, also the company or the supplier of the panel in the end. So for those of you that has the opportunity to go to Oslo and see Voldsbø Skole, it's well, it's super cool. We got one negative reaction on it. I don't know if this can understand that. We are talking 2023, 22, 23. Look at that colors. What do you think? Looks like military. So neighbor has complained. And obviously because of the war in Ukraine. So this is important. The economy is good. People tend to think that the facade is expensive. Well, yes, it's not for free. But if we compare it to another facade, if you think we have a facade, it should look like this. Then change it with PV. Then you have a marginal cost. So is in the first example there, let's say that the PV costs 1,250 kroner per square meter more than another facade. Then think that you can produce 80 kilowatt-hour per square meter. Then the cost of power is, energy is 50 øre. That is not expensive. It's good economy. And if you will calculate payback time, well, you can calculate 3 kroner per kilowatt hour. You can play with other numbers, but 5.2 years is not bad. It's good. So to use PV in facades in cities might be very economical or profitable. This is an example from Asko-Hedmark. You see that we are producing more energy per square meter on the facade than on the flat roof. And we also found out that the price for facade is actually cheaper than on the big roof. If we have everything is, it is easy to mount from the ground using a Saxe lift, if you know what that is. You can see that the yellow area, the square of the yellow area is bigger than the green one. And then you can see the production per square meter on the left side. The blue bar is the roof, the red one is the facade. So, and that's also perfect balance, because then you can produce more energy in winter. You can also produce more energy in the morning and in the evenings. So we have better production balance. And this is good. This is the first time a finance director called my manager to visit, because we have invented in our sister company, INOS, we have invented a system that we call a weight watcher. Means that it will measure the weight on the roof with a lot of snow. Then an alarm goes off and we turn on power and send that up on the roof. Weight watchers. So in 2018, it was a heavy snow load on the roof in Oslo. And these days, the snow load are much higher than it was before. And roof started to fall down, not good. So what do we do? Well, remove the snow, heat cables or solar panels. And what we also do, we turn on field by field, because we cannot send all the power to the whole roof. That would be too much power. So we just limit it to one field, second field, third field, etc. So this is from the downtown Kjøp Center in Porsgrunn. It was an old factory. And from time to time, they have to send the people to shovel snow off the roof. And that, some years ago, we sent boys from the football team up on the roof. That is not allowed anymore, because you have to be careful with people. So, what did they get? Well, we removed snow from the roof. We also solved the weight problem, because if the weight is too high, the roof can fall down, or we have to evacuate the building until the snow load is less. Then we also get rid of all the water. So it's not just to turn on the power and melt down. It would be a lot of water, and that water need to get somewhere. They have to be drained. Need to be simple in use. You also need to control the weight on the roof, so we have sensors that always measure the weight. And then when I steal slides, I also have to read it more carefully, and I found out that we forgot something on that slide. So when you're shuffling snow, you damage, or you might damage the roofing. That's not good, because then it will be a hole and we will have problems later. then no worries about where to place the snow, because when you're shuffling the snow off, where should you shuffle it? You not do it there because it's people there. There we have trucks, a lot of challenges. And then you don't need trucks to remove the snow. So it's for an urban environment, this could save a building's life. So if the building, the roof is too weak, you need to, well, demolish the building and build a new one. You don't have to, because you can put solar panels on the roof. It sounds crazy, but it works. Yeah, in this center, you have approximately 1 megawatt peak pounds. We have also larger plants other places, but this is just an example. And if you want to understand more of it, you can go to YouTube and look at the video we made together with the customer. So he told, or he is telling how perfect this is. Yeah, I think that was, yeah.
Thanks a lot, Geir. Many challenge you had. So maybe later on we have a round discussion. So yes, at the end of the session, now is turn of Multiconsult, Ida Brin and Tobias Christiansen. Ida is a discipline director for indoor environment at Multiconsult with a PhD in ventilation and energy system. She has extensive experience with complex energy system and axiom designs. While Tobias Christiansen is daylight and energy consultant at Multiconsult, specialized in optimization of energy and indoor environment. Please, the floor is yours. You are two, so one use this microphone, and maybe you pass together. I don't know how you divide the presentation. Yeah. Please, floor is yours.
Thank you. Yes, now we have talked a lot about solar energy, but now we are moving over to light and to some challenges we see with the right to light. How do we use this? Right to light is in some countries they have a law to protect people for their right to have light. In England they have that for a long time, and I also found that in Japan they have that kind of right. But as the situation is in Norway, the law is quite weak about these things. If you look into the regulation, we see that there is a basic law that to take care of the fire safety, and there's also written that we need to ensure light and air between buildings, and there we have some kind of a rule that says something about the distance to the neighbor border and the height of the building. But this applies for domestic areas, but it seems that when we are densifying cities, this rule is not applied anymore. And if you look at the rules for daylight, we have a rule in the Planning Act, and for the daylight percentage, daylight factor, it's 2%, and that applies to the building you are going to raise. So if you are raising a building, it has to have 2%, but it doesn't say anything about how you the consequence for your neighbor buildings. And we have also a workplace regulation, and the workplace regulation is the same as in the Planning and Building Act, 2%. So, but we have not no rules that say if you raise a building, you should not steal the daylight of your neighbor. So that is still not protected. So we have a situation. This is from a new area in Oslo, very close to Majorstua. And this is how they raise buildings. Those Norwegians can perhaps see where it is. You can see the building behind. I think it seems that we have forgotten this section 29.4 when we're densifying the cities, and we say that we want to make a climate action, so therefore we have to densify. But what about the good health for people? What about the sustainable cities? And what about the increased inequalities for people that have to live in these areas? And then I will present two stories about a fight for light. This story started in 2016. Our client is, they have this building you see here. And the other neighbor around to the right there, they wanted to raise 6 floors, as you see shown in the picture to the right. And this case has been going forward back well, it's 6 years, 7 years, and the building and planning department in the city, they did not want this, but the politicians, they said, we want this to be built because we want to densify the city, and that is environmentally right. If you see a section of the situation, you have our client is here, and this is the old the neighbor building as it is now. And here you see the view up to the sky up here. And they wanted to put up 6 stories, and then you get this view to the right. And those of you that are not well known with daylight know that there will be very daylight down there. And then after many years, we asked Barbara Matusiak at NTNU to help us, and just to take the strength in the argumentation, and also to propose some new ideas. And she came up with this idea: you can have a building like this, and then we got an architect in, and they proposed this alternative. So we calculated the situation. This is a daylight situation in our client's building today. This shows the area that has enough daylight according to the regulation, the green area. Here is a situation when the neighbor built their 6 floors. It's only on the 2 upper floors they have enough daylight, nothing down here. And here is a situation with a proposal from Barbara. As you see, it's a very good idea, and still they are able to build. But what actually happened here, that after 7 years, they withdraw their proposal, they gave up. So it was really a success, the best Christmas gift ever for my client, I think. But the thing is that you have to be a billionaire to win a fight like this, because he has spent millions on lawyers, on people like us, on communication people. So this is really not fair that you have to be that rich to win a case like this. So now we have got a reputation on this. We got a new case, just a few blocks away. This is the client here is, they have this area here, you see into the backyard. They own this building here. You see it's a quite dense backyard. And now the neighbor in this building, they want to improve or increase their area, fill up the backyard that you see here. And they have made a calculation, and they came that all the data here in this backyard is of course it will only be minor changes if they build here. So they calculated, actually that is the client's the neighbor's calculation, that this is a change of the vertical sky component, and it's only minor changes, so it doesn't have any impact. But if you see the relative reduction, it is like this. And I think it's like saying if you have a poor sight, if you are half blind, if you give a little less ability to see, it doesn't matter. So I think it's a way of arguing within light is very strange, and the right to light I think is very poorly understood. So we need laws, I think, to protect this human right for light.
Thank you. I will talk a little about how we can address this issue as well. So we can look at the impact on neighboring buildings in projects, like you see here in the figures, where there are 3 alternatives for the option ranging from design option A in the middle, and we have the current situation on the top. Design option A, where we have 7 stories, and design option B, where we have retracted facades you see on the bottom, but less. So these kind of studies can give us an indication on the impacts without needing to know anything about the interior of the evaluated neighboring building, which could be difficult to get access to when you are doing a project. So these are kind of tools to check the neighboring buildings. So do solar energy have the right to light? There's been some cases where planning permissions have been overturned in court, actually, on the basis that electricity generated from solar panels was helping migrate climate change. So this is really good to see. But daylight also is a human right. So if energy can, in fact, if needed, be produced elsewhere, but daylight access cannot. So it's important to address that issue as well. So also a solution might be regulating the airspace on the building plots, like we see here. So this is indicating volume where you can build within on a building plot. This can also implement existing regulations like we talked about previously, with the building height, distance from plot, boundaries, and visualize it in 3D models. So 3D regulation is also an ongoing project in SOC 5.0 formatting, but it's not mentioning solar access and daylight. So we need regulations to protect building owners' right to light. There must be a requirement to meet daylight in urban space regulations. And how do we secure the right to solar energy as well? Need to be addressed. So that was Mervyn from us. Thank you.
Thanks a lot to both of you, Ida and Tobias. Very interesting presentation. All presentations we had so far are really very practical. So I'm very happy, especially for many of you that are here to learn how to design buildings, which are the challenges and so on. Okay, we move now on with the last presentation before the break. Is Yuri Kanters. Yuri Kanters is associate professor at Lund University, and he's educated as an architect. His research interest is in solar energy in cities and building, as well as circular building design. I'm really very happy you are here. Thanks a lot. And yeah, we have many interests together, so I'm looking forward to hearing from your presentation.
Yeah, thanks, Gabriela, for the introduction. So I'm going to, I mean, of course, that Gabriela did this clever and put the things that have in common with each other after one another. So I'm trying to kind of highlight the Swedish perspective on urban planning and planning for solar access. But first, I thought maybe it would be interesting for you to give an idea of the Swedish planning and building design perspective. So I have no idea if it is similar or to Norway or not, but it typically starts with there's a piece of land that is owned by the municipality or by another third party. And the next step in the process is that the urban planners at the municipality or cities, they have in Sweden what is called planning monopoly. So they are the only ones that could design a zoning plan, setting building heights, roof inclinations, etc. Then typically the land is being developed by a real estate owner, and these real estate owners, they have to comply with the Swedish building code. And in the Swedish building code, there are lots of requirements, and amongst others, we have daylight requirements, as was mentioned before as well. We also do not have right to light, so that's also a very good fight to, in Sweden as well. And there are also requirements on, for instance, the maximum energy that can be used per floor area. So then typically the building gets sold after it is constructed, sold to the final user. So there are lots of different steps here, lots of different actors. The final user is often quite disconnected from the whole process. And I will be mainly focusing on this step here. So what can urban planners do to make sure that there is enough solar access when they start working in the urban planning phase? We performed a survey amongst the urban planners in Sweden and asked them, so how do you work with solar access? Well, first of all, they said, well, there is no really definition of solar access. So for us, solar access could mean different things, right? So it's a bit what Maria also said in the Task63. We look at active solar energy production as one thing. We look at daylight, but we also talk about direct solar access. So using the sun directly, just to be in the sun, and which is a very kind of quality of life. So since there is only like the daylight indoors is regulated in the building code, urban planners have to make sure that the real estate developers actually can comply with the building regulations. So the first priority is to have daylight indoors, or make sure that the zoning plan that they develop or design ensures like a good daylight indoor quality. And then urban planners also are normally very concerned about having access to the sun outdoors. So making sure that there's a livable city, like squares without direct solar access is not a very good square, right? So, and that also, of course, translate into financial value. So if you would have I don't know, outdoor seating without direct solar access, it's not a very attractive place to be. And then the lowest priority, I would say, in this context here is the active solar energy production within the urban planning phase. So they feel a bit disconnected from this part here. But yeah, I hopefully can show you that, of course, the urban planners already set the framework for all these things already in the very beginning. So there are not necessarily established routines for making sure that there is enough solar access. And they also very often do not necessarily have the competence or the right tools to actually work with solar access. So they would like to have access to tools that can do this. And they are not necessarily interested, for instance, in getting all the numbers like, you know, vertical sky component that was shown here, but very much kind of indicating what are the weak points in the zoning plan that we designed. I show you some examples soon. And of course, it would be nice if it can also kind of take other parameters into account, like microclimate, etc. So an example of a detailed development plan, I don't know how it looks in Norway, but it's a legally binding document. So it's a very important document. And for instance, in the color coding, you see different functions, like the red are schools in this case, and there is a residential area in yellow. And you can set roof inclinations, building heights, all kinds of different things. And those kind of settings here in the detailed development plan, they are very crucial for implementing active solar energy systems, right? So if your roof inclination is 45 degrees or 20 degrees, that's going to be quite a big difference. Maybe in a place like Norway as in Sweden, has a very it is decisive for your energy production. So the city of Malmö wanted to try to come up with a detailed development plan that was beneficial for locally produced solar energy. So I was involved in designing this detailed development plan together with the city. And that was from 2016 to 2020. So it's located in Hyllie, which is the first train station if you come from Denmark. So the most southern part of Sweden. And this was the first detailed development plan that we developed. So you can see here some building footprints, in yellow, the residential buildings, and in red is the school again. And this is how the urban planners did, like that. This is the normal procedure, how they work. So they designed the buildings, and then we start talking about, like, so how can we make sure that we create good conditions for, in this case, implementing PV systems. So then we start talking about, like, what kind of requirements could we put in the detailed development plan that can make this easier. So for instance, what you could set is the roof inclination, for instance, setting a minimum and a maximum slope of the roof. That could be beneficial then for the production. But you can also say that you could, in a detailed development plan in the Swedish context, set building materials to be used. So you could, for instance, say that, okay, a building needs to have yellow bricks, right, as a facade material. So if you consider PV as a roof material, then you can put this in the requirements. But then, but you cannot force the real estate developers to actually plug it in, which I think is pretty interesting. That's not allowed. But then the city didn't want to go this far. And in the end, what we ended up with was a detailed development plan describing the minimum maximum slope of the roofs and the fact that you could put up PV, but they have to be integrated into the architectural design of the building. So then the first building that was constructed had a very small PV system on the roof, which was not visible. So, and this has different political reasons. I'm not going into that. That will require another presentation. But after a while, the city kind of noticed that real estate developers got very interested into the concept of actually integrating PV more architecturally, you could say. So this is one of the latest buildings that have been constructed. It's a mobility hub designed by Foyab, where you can see green PV systems integrated into the facade. So it became quite popular for the real estate developers to actually start thinking about integrating PV. So then we continued working with the urban planners, both in Malmö and in Lund, which is neighboring city, smaller than Malmö. And I would say also, which I think is interesting to mention in this context here, is that the bigger cities, they have maybe the right competence within the city to think about daylight and have established routines, maybe can buy licenses for simulation tools or whatever. But the smaller cities or even smaller municipalities, they do not have this competence. So we help them to kind of make sure that they already in the very early design stage of the urban planning take the right decisions. So we discussed with them how if the design detailed development plan was good enough, so there was enough daylight indoors, and we also discussed the solar access out on outdoor spaces, and also active solar energy production. So basically this is the workflow. So the urban planners provided us with like 3D models of their detailed development plans. We ran some analyses, and I think the most important, the analyses themselves were not super advanced, but it was more than the urban planners normally had access to. So we had a discussion with them. I think that was the most important part of this workflow here, and discuss the results of our analyses. And then if they were satisfied, then they went on with it. If they were not satisfied, we could reiterate different loops here and trying to improve their zoning plan. So what kind of analysis did we do? For instance, we looked at daylight provision. So the Swedish building code has the requirement of a daylight factor of 1% at the darkest wall. But it's not super relevant, but we just wanted to show what happens if you have a different window to wall ratio. So in the urban, I should also mention one thing, like in the zoning plan, the urban planners do not set any window to wall ratio or openings or windows. That they leave that up to the real estate developer to kind of design, and their architects. So we said, okay, what happens if you have a 10% window to wall ratio or a 90% window to wall ratio? What happens? How easy is it to comply with the building regulations? Or we also run vertical sky component analysis just to show what are the points in the zoning plan where it might be very hard to actually reach good daylight indoors, very similar to what Tobias and Ida just showed. Well, we had, I think, the most discussions on direct solar access outdoors. So the city of Malmö just had a kind of internal requirement saying that 50% of all the courtyards that we designed should be sunlit at the 21st of March, if there is sun, obviously, but let's assume it is. But lots of the urban planners that were involved in this process, they didn't really like this requirement, because it means if you would have a very long courtyard, you will have you will actually meet the requirement pretty easily, but not that's not always the most favorable form or shape. So we looked at other time resolutions. For instance, looked at whole 21st of March. And there is an old Swedish requirement or recommendation, saying that you should have at least 5 hours of direct solar access on the 21st of March for places to sit or to play, for instance. And here you see, if you stay within this black line here, those places have more than 5 hours of direct solar access. And I said, okay, well, maybe that's good. And keep in mind, there is no legislation on this. So we had to kind of together find out what is a good quality. And here we looked at the annual direct solar access, and just so we also like kind of together trying to find out what is a good metrics and what are good thresholds. Those are exactly the same analysis. but just visualized in another way to make it easier to understand the result. So for instance, if you would have an unobstructed plain without buildings or trees or whatever, those are the maximum, then it would be 100% of the possible hours, right? But then we categorize them, for instance, 0 to 25% of the possible hours, or 50 to 75%. So the left picture is exactly the same result, but it's just visualized in a very different way. So we were together looking for what kind of feedback do you want on your zoning plan. And we also run very quick active solar energy production. And if you match that with the floor area, you could take kind of a template value for the energy use. Then you can calculate quickly like how much you can cover if you would potentially implement PV systems on all of these colored areas. So, and that would also, of course, affect the urban area. Like if you would implement PV, if you have to implement PV on all of these surfaces, it will obviously give a very different image than if you just cover, for instance, the roof. And then, of course, you have like a lower coverage. So lots of things are still unknown. As I said, only daylight indoors is regulated, but nothing else. So next steps in our search here is, for instance, my colleague Agnieszka here, looking at what kind of thresholds, like the 5 hours that I mentioned on the 21st of March, is that actually something that people want, or where does it come from? Like, is 5 hours, is that good? Or is it maybe 2 hours? We don't know. So that's under investigation. So with that, I thank you for your attention.
Thanks a lot, Yuri. I just invite all the speakers to take a seat. Now we move the chair here. Just have some questions. There is any question from the audience? Okay. Lady first. Yeah, okay, please. Oh.
Hi, I'm Nilufer. My question is mostly from Yuri, talking about daylight. In the conceptual design stage, what do you think, which metric is better to work with, like to like form about the forming and the shape of a building mostly?
Yeah, it's a good question. I think it's very related to what Tobias also showed. It's the vertical sky component. It's a very quick way of checking if it's how easy it is to get good daylight indoors, I would say.
Okay, was another question from you. Yes. Can you pop your microphone? Thanks a lot, Amin.
Thank you. A question for Yuri, as you're a very good expert of solar access. So we would like to maximize, to create urban design that maximize the solar access, for instance, to open courtyards, yes. But what about the problem also of overheating during the summer? Because of course, I can understand that during winter, we would like to maximize this solar access, but no. We also have to find a good compromise between solar access in winter and also protection from solar access in summer.
Definitely. This is also, I mean, a problem in Sweden and I guess in Norway as well. Like in the summer, there could be heat waves. And then, of course, if you are maximizing to have the most amount of direct solar access, that's not a very good strategy. So you have to make sure that there are differences in the courtyards, like there are places for shading and that there is places for actually enjoy the sun. So we definitely take this into consideration. Yes, you're right about that.
So, yeah, thank you very much for your presentation. I have actually 3 questions, so we can just open up. No, yeah, exactly. I have one from Robert, one from Gear, and one from exactly the daylight. So from Robert, so yeah, very impressive project, this building that we are in. So my question was that did you like carry out any like demand side management? I saw that you have this like super capacitor for buses and like connection with other buildings. So on the demand side manager and like energy consumption behavior of the end user, did you do any like investigation on that side, or like the design of this microgrid was like mainly on the production side?
I apologize, but I don't have enough information about that because I haven't done that project. So I don't know what kind of analysis they have done in regards to the consumer side there.
Yeah, because it would be so interesting to, I don't know, just schedule something for this, because there's like these bottles that they are going to be charged. So to suggest some, I don't know, like schedule for charging.
Yeah, I know the control system that I showed is a ABB system, but I don't know how the details there on how they manage load, for instance, and when do they start the battery, when do they start discharging. And I don't know either if it's coupled with the economic model. Of course, that's a very nice you can discharge a battery when the electricity price is high, for instance. I don't know where they are. I don't know where the project is in regards to all those questions. Yeah, so I don't have a good answer for you.
Thank you. And then from here from Busan, yeah. I know your company from like 2018 when I started my like PhD. I got a lot of data from Busan, so thanks for that. So, and so my question is, one of your presentations, you said that so it is like this, the production of the facade and roof are so close. So I assume that was just south facade, so not like east facade. So the production for south facade, I assume, is so close to the production of the roof, I think.
The facades was southbound in a way,
yeah,
but not directly south.
Yeah. And the other question that I have, I know that you, I would like to have like a bit more, you comment on like, from what side, do you have any like a number in your mind that's from what side, over what side you decide to participate in a solar project? Like is it 100 kilowatt peak, or I don't know. In Houston, do you have something like that? Because I know that Houston is so busy with, I don't know, with like mainly large scale solar like project in urban area. But do you have any like limitation that you don't go for less than that for solar project?
Very good question. Do you have more questions? You know that it's a little bit difficult to answer, because when you're building up, let's say, a market, it could be in Trondheim, I'm in Bodø also sometimes now. Let's say a plant of 100 kilowatt is interesting. But when we are growing, as we do in Oslo, then 100 kilowatt is nothing.
Yeah.
So it depends on the market. So, and we are aiming for the big project, and we are building up, ramping up a company that are super efficient with logistics, with getting components, putting components on the roof, on the sales. So the better, the bigger, the better. But obviously we have to build the market.
And just one more question quickly. So how, like, what is the installation, average installation time, like, for say 200 kilowatt peak facade like project in Norway for Fusen? How much is it? In average, I know it's just varies a lot.
Let's say I did a facade at Chile last year in the winter. It's difficult to say because I needed, I couldn't lift myself directly up. I need to use what you call a boom lift. I spent 1 week for 100 kilowatt peak. But normally, efficiently, we can do 200 kilowatt peak in 1 week. With 2 men. Let's say 3, because we need one guy at the bottom, at the ground.
Thank you.
Typically.
The last question from right to life, from like Yuri and the occupants of presentation. So very interesting topic. Thank you for that. So I think that I just wanted to see your point of view about this, that the right to life like takes precedence to like active solar production, because normally when we have this urban design, urban planning, I don't know, urban area, the lifetime of this urban area is going to be, I don't know, 100, 150 years or something like that. Why, if we design like solar production for this neighborhood, it's going to like last for 40 or 50 years. It's good to keep in mind that when we like this design this daylight or right to life, even if we don't have this like active solar production right now, it's good to keep the doors open for like renovation if it's going to happen in 40 years or 50 years or something like that. So what do you think about that though? How should we just ensure that this is going to happen in terms of renovation and so on?
Yeah, so I agree with you. We have to take this into account when building, and like we showed in our presentation, it could be like these volumes that you show in the regulations. So if you want to buy a pot, you know what's going on around the place, maybe into the future as well. That could be a kind of a solution to see what's the limitations of the buildings around your plots, for instance. So maybe one solution. Yeah. Yeah.
So for instance, in the US, you have lots of these solar easements, so that are going to protect your system, right? So your production of your system. So for instance, they say that if you don't obstruct the different kind of angles, then and between different times of the day, then your production should be fine. Otherwise, you have to be compensated for it. So you see this more and more in different countries, but for now, right now, mostly in the US. But I have seen some court cases also in other countries like South Africa and Australia, where they actually went to court because their PV panels were obstructed, or like they planned to get obstructed, and so they kind of miss out on production, right? So there should be a compensation. So it's I think that therefore it's very good to already start very early to think about protecting, or you kind of establish a base case, right? If you develop a new development, or a new area. So there's a base case, and then from there you start thinking about it. And especially when you start densifying things, then it gets very complicated. And so that's why I think, especially in densification projects, then it's very important to do this.
Okay, there are 2 questions from the online audience. One is for Tobias and Ida. Paul Rogers say we are doing a lot of similar work, right of light in Sweden. This has been discussed with the code authorities, but political will is relatively weak. Do you have a strategy for moving this initiative forward to the politicians?
What did I say? I think our strategy is to lift the question to the public, into the media, start with that, to get people aware of it, and to get an opinion among people, because I think we have to start with that, and then the next step can be the lawyers and the politicians, because now I think very few people are aware of this situation.
Yeah. Thanks. You want to add something, Tobias?
Yeah, just quick. I guess it's like kind of similar with the energy grading system. It started somewhere. Maybe in the future we can have a daylight grading system, so the end user knows what they are getting. So
yeah. This last question from the online audience for Yuri. Are there any recommendation for what is good as area to install PVs, like a matrix that called SAFAR, for example? And if yes, have they been updated to current energy price of PV?
Yeah, I mean, where to put, which metrics to use and which thresholds is always very, it's a, I don't, it's a long debate, I guess. So irradiation doesn't really, well, it changes a bit, but not necessarily too much. So in different countries, you can apply different thresholds, but I guess that with new, so normally you kind of calculate with a certain, what should I say, like a lifespan of a PV system, and then you can calculate, for instance, say payback time should be under 10 years, then where's the threshold be of the irradiation? So, and then this has changed rapidly now. So maybe it's time to update these thresholds now. So irradiation, annual irradiation, yes, that could be a starting metrics, and that's very well used, I would say.
Thanks a lot to Yuri, Tobias, Robert, Ida, and Gabe. I think we can end the session, the two sessions now. I think we will have a break after around the 6 presentations. There is coffee and cannibal outside, and we come back at 55 past 10, yes, in 50 minutes. One thing more, there are PhDs and students that they have printed the poster of their research related to solar energy from different countries. So there is a poster session now and also at the lunch break. Enjoy the break. We see each other in 50 minutes. Thank you.
I know we used to like
You can,
program.
we can stop the record now. Maybe we stop the recording now. And... Maybe I need to.
Wait, it comes up.
I need to close and then stop it. Stop recording. Stop recording or pause?
Stop post recording because
Pause?
yeah.
Otherwise, maybe
Otherwise it makes a new file.
yeah, but that's what I mean. Maybe you can shut session one and
Okay, that you can
stop
recording. Yeah.
and then it's